Welcome students to our video notes lesson on section 5.6, where in this video we're going to go through all the functions we've learned this entire year in Algebra 2. We will be graphing all the functions. And when you look at this outline, I hope it makes you proud of all the content we've covered this year and all the information you have here at your fingertips. Let's get started with this linear one. What we're looking at here on this first page are all the parent functions. So the parent function for a linear graph is very simple. It's just y equals x. Whatever x is, y equals the same thing. So when x is -2, y is -2, and so on. So when we plot these points, we can see that there's a slope of 1 between them, a constant slope. And I could continue the points by continually going up 1 and over 1 from point to point, or down 1 and left 1. And so that creates the shape of a line. If you were to think of this in mx plus b form, or slope-intercept form, we could say, well, this line had a slope of 1 and a y-intercept of 0. What makes linear functions so unique is the fact that they have a constant slope, which you could also think of as a constant rate of change. So you could be given any point and the slope. So you need to know the slope and any point. In this case, the slope is 1. But I could have started this line from maybe this point right here. Just any point, as long as I know one point and I could have a slope of 1. So I'd go up 1 over 1, up 1 over 1, or down 1, left 1. And I would basically still have the graph of the same line. So linear functions are unique. All you need is one starting point and the slope, and you can graph the whole line. So this one does not require transformations to sketch the graph. Now looking at our absolute value function, that of course is the one that has the bars around x. And what that's essentially doing is just for the y coordinate, you're just taking the absolute value of all the x coordinates. So if x is negative, it's just turning it positive. But for all other values of x, like 0, 1, and 2, they just stay the same, because the absolute value of a positive stays positive. So this function was unique because the range could only ever be a positive number, no matter if I plugged a negative in for x. So my domain could go left and right, but my range could only go positive. It could only go up. So when I plot the points, I see that they go up on the right, but also up on the left. It had a little bend right here at what we call the vertex. Now the vertex in this particular function is happening at 0, 0, because this is the parent function. You could say that for all these parent functions, their a values are 1, their h values are 0, and their k values are 0. And this is true for all the parent functions. And that's including this one here, right? I've got a 1 in front, nothing's in the absolute value with x, and I'm just adding 0. So that's why the bend, or the vertex, is happening here at 0, 0. Now if I'm given a different hk, so this would typically be at your hk, then I know that my bend will be there based off the parent function. So this function also does not require transformations to sketch its graph, because it also, like the linear function, has a constant slope. Constant slope, or a constant rate of change. Now the slope, though, in this case, is both positive and -1. So on the right side, your slope is whatever the a value is, which in this case for the parent function is 1. On the left side, it'll always be the opposite. So notice that on the right side, it was going up 1 and over 1 between point to point. But on the left, it's actually going, if you start here, it's going down 1 over 1, down 1 over 1. Or if you start from the bend, or the vertex, it goes up 1 and left 1, right? So it's kind of an opposite slope, and it creates a bend right in the middle. But it still has a constant slope, meaning as long as you are given the vertex, as long as you have the vertex, and you know the a value, which gives you your slope, the slopes will be plus or minus the a value, then you just plot your vertex, and then from there you use your slope to go up on the right and on the left. So at this point, I want you to get out your highlighters, and I want you to highlight the linear and the absolute value and the fact that they both have constant slopes, because that is something that makes them very similar and also very different from all the other graphs. These are the only graphs that are going to have like straight lines in them. So that brings us to the quadratic function, where we are squaring x. So sometimes we also call this function the squaring function. This is any equation that contains an x squared. Of course, the parent function is just plain x squared. A is 1, h is 0, and k is 0. So the y value is simply just taking the x and squaring it. Now, as a result of squaring numbers, these negative x values, when I squared them, became positive. So this, like the absolute value, is unique in that the x can be anything, negative or positive, but the y values come out positive only for this quadratic function. So when you plot the points and connect them, again, you have a graph that does not go below the x-axis. It has like a bend in the middle, which again we call the vertex. And at that point, it bends back up, and so both sides face up. So now looking at the cubic function, the one where we are cubing x, when I take a negative number and raise it to an odd power, so now I have 3 factors of -2, I end up with a negative result. So unlike squaring a negative, right, squaring a negative turns it positive, cubing a negative will keep it negative. This is going to turn out to have a lot of significance when looking at this graph. Same will happen with all the rest of these. So when I find all these points, I can see that the y values are negative and positive, and when I plot them, I can see that not only will they go up, but they will also go down. Because x is allowed to be negative, which means I can have points that go left, and y is allowed to be negative, which means I could have points that go down. So the right side almost looks like a parabola, except the left side goes the opposite direction. And it creates instead what we call like a squiggle, or a lazy S, I think was one of the terms used, but it's this kind of bent parabola, right? And then this point in the middle, we no longer call that a vertex, we call that an inflection point. So now what I want you to do is get out a green highlighter, and I want you to highlight linear again. So linear is going to have 2 highlights. Yellow because it has a constant slope like the absolute value, but green because like the quadratic and the cubic functions, it is a polynomial function. So the linear function is a polynomial with a degree of 1 because the power of x in the equation is 1. Whereas a quadratic is a polynomial with a degree of 2. And the cubic is a polynomial with a degree of 3. So the linear and the cubic could be considered odd degree because linear has a degree of 1, cubic has a degree of 3. So we can think of these as being odd degree. So notice what odd degree polynomials have in common. They go up on the right and down on the left, at least for the parent function, right? The linear did the same thing, up on the right, down on the left. That is because both their inputs and outputs are allowed to be negative. So they go up on the right, down on the left. Now notice the quadratic had a degree of 2, so you could say that it's an even degree. Now the absolute value is a degree of 1 because x is to the first power, but it's still considered to be an even function. An even function because if you notice the absolute value and the quadratic, they both go up on the right and on the left. Up on the right and on the left. And you could say that they both have what we call y-axis symmetry. There are, in fact, a lot of similarities between the quadratic function and the absolute value function because also these ones had ranges that were only positive, right? They weren't allowed to go below the x-axis. The difference between them, though, and this part's important, is the quadratic graph is curved because it does not have a constant slope, right? The absolute value has a constant slope, so that makes it straight edge with a corner. The quadratic function does not have a constant slope. That makes it curve, right? You can see here it goes up 1 over 1, But then to get to the next point, it goes up 3 over 1. So it's not a constant slope. And that's also the difference between a cubic and a linear. So they're odd, so they go kind of in the same direction, up on the right, down on the left. But the cubic one is curved because it does not have a constant slope. Linear function has a constant slope, so it forms a very straight line. Cubic function does not, so it forms this curvy shape. So now moving into this semester, we were looking at square root functions and cube root functions. So for the first time, we had functions where you could not plug in -2 to 2 for your x values. So I want you to take out your highlighter again. If you have a different color, I'm going to use blue, and I want you to highlight square root, cube root, and logarithmic. Because if you look, those are the functions that are not plugging in your typical -2 to 2 x values, right? If you look at all our other parent functions, that's what we use for x. -2 to 2, -2 to 2, -2 to 2, -2 to 2, -2 to 2. This one we throw in some extras, but it still goes from -2 to 2. These are the only 3 that don't, and I'm going to have you write down this word. Now, you may not know what this word means yet, and that's okay because we're going to address it. But these functions are what we call inverse functions. These are all functions that are doing the reverse operation of one of our other parent functions. The square root function is doing the reverse operation of the squaring function. So instead of squaring, I'm square rooting. So the kind of x's we plug into the square root function are perfect squares, and even more specifically, positive perfect squares. Because we remembered when we squared functions, the result always came out positive. So the square of a number is always a positive value. And since we're plugging in perfect squares, we can only plug in positives. So this was kind of the first time that we have a domain that's restricted to just positives. Then also, because we're only allowed to take positive square roots, right, this is known as the principal root, our y values also only come out positive. So we notice that when we plot these points and connect them, we can see that from this starting point, so 0, 0 is kind of like the starting point, which normally is our hk. Of course, here in this parent function, h is 0 and k is 0. That's where the graph will start. And then from there, because I was only allowed to plug in positives, the graph could only go right. And then because I was only allowed to take positive square roots, the graph could only go up. So it kind of forms what we call this eyebrow shape. Now just for a moment, I want you to look at the last 3 points from our quadratic graph, our squaring graph, and compare that with our first 3 points on our square root. If you notice, the numbers that were used to be the y values, 0, 1, and 4, have become the x values, 0, 1, 4. And the numbers that originally were the x values have now become the y values. That was 0, 1, and 2. Because the square root is basically doing the reverse operation from squaring. So that's essentially what an inverse function does. Now if you notice, the points 0, 0, 1, 1, 2, 4 are right here on the squaring function. Those same points are seen here on our square root function, only the 2, 4 has reversed to become 4, 2. So you can see that this eyebrow basically comes from this half of the parabola, where I just switched the x and y, and so now it's kind of going out to the right instead of up. But those are essentially the same part of the graph. This one is just doing it in the reverse order. So now looking at the cube root, this is where we are taking the cube root of all of these x values. So I was allowed to plug in negatives, right? I was allowed to plug in negative numbers that were perfect cubes. And then the y value just cube rooted all of them. So notice that x was allowed to be negative and y was allowed to be negative because this is a cube root, an odd root. So earlier we noticed that when I took -2 and multiplied it to itself 3 times, the result was still negative. That's how we know that perfect cubes can be negative. And we can also see the same relationship here between a cube root and a cubic function. Notice that again, what used to be x values, -2, -1, 0, 1, and 2, have now become the y values, -2, -1, 0, 1, 2. And what used to be the y values, -8, -1, 0, 1, 8, have now become the x values, because the cube root is just doing the reverse operation or the reverse order as a cubic. Instead of cubing, we're cube rooting. So it's just reversing the order or switching the x and y's. So when I take these points and plot them and connect them, I can see that same shape of the squiggle that we saw back in last semester with x to the third, only this time instead of stretching up and down, because this point would be 2, 8, and this one down here would be -2, -8. Those have switched, right? Now this is 8, 2 over here, and this is -8, -2. So now it's stretching right and left. But it's essentially that same type of shape, just in the reverse order. When you compare the cube root, which is odd, to the square root, which is even, you can see that unlike the square root, this graph can go right and left, right? X was allowed to be positive and negative, and it's allowed to go up and down, because my y values also, again, were allowed to be positive and negative. So this graph is more of just a sideways squiggle. Now moving to our exponential function, of course remember, more generally, we would think of this as y equals any base b to a power of x, as long as the base is positive and does not equal 1. So this is one example, right? This is where the base would equal 2. So this gives us one idea of a parent function, but remember for this one, the parent function will vary based on the value of your base b. Okay, so for this function, we are going to think of these x coordinates as the exponent, right? This is the first time that we've been able to keep the base constant but allow the exponent to vary. So the base is always going to be 2 in this particular case, but I'm raising it to these other powers. And it's important to keep in mind that when you raise a number to a negative power, it doesn't make it negative. It just takes the reciprocal, so it flips it over and makes it 1 over 2, and then squares that. So this has a unique feature, again, where the y ends up being greater than 0 the entire time. In fact, the y value will never equal 0 because there's just nothing that I could plug in for x to get 0. There's just nothing that will work. Even if I plugged in, say, 0, we did that right here, 2 to the power of 0 is 1, right? That's not 0. Now I noticed that when I plugged in these negatives, these numbers got closer to 0. So maybe I could plug in a number like -100, right? But even when I do that, I still end up with this positive number because I just flip over the 2, make it 1 over 2, and raise that to the power of 100, which is like a crazy big number. And it gets closer to 0, but it never actually quite equals 0. So this function is very unique in that it sort of approaches 0. So I want you to get out another highlighter, whatever color you have left. I just have this pink one. So for the exponential function and also for the logarithmic one, I'll just put it here, and for this reciprocal one, these functions are unique because each of them has asymptotes. The exponential function has a horizontal asymptote, meaning it goes left and right, and that is at y equals 0 for the parent function. That's because my k value is 0. And so when you plot these points and look at them, you can see that as the x gets more negative, so as x is going this way, right, -1 to -2 to -3 to -10 and beyond, these fractions are going to get smaller and smaller and really, really small. So they kind of get closer to 0 on this left-hand side, but will never actually quite equal 0. There's no exponent that I could raise 2 to make it 0. So that's what sort of creates this horizontal asymptote, and it really more applies to the left side, the part where x is going to, we say x is going to negative infinity. It's getting more and more negative. On that left side is where you will really see y getting closer and closer, but never equaling 0. Although we usually just dash the line all the way through. But then this other thing is happening on the right side that's totally different. On the right side, the y values get pretty big pretty quick. It goes from 1 to 2 to 4. The next one would be 8 if I kept going, and so on and so forth. So it shoots up really fast on the right side, but kind of slowly inches its way closer and closer to 0 on the left side. So a very unique type of shape. So then when you go and compare that to a logarithmic function, you notice that, wait, I notice a reverse operation happening here. So a log base 2, by definition, this is the base. Y is the exponent, right? The result of the log equals the exponent. And now x is the result. So y equaling the log base 2 of x is the same thing as saying 2 to the power of y equals x. So look at the numbers we have here written for x. They are what used to be y, right? 1/4, 1/2 right here, 1, 2, and 4. These are the old y values. The y values when I was doing 2 to the power of x, because that's what these really are. X is equal to 2 to the power of y. These are what you get if you raise 2 to a certain power. The y value, which is what the log equals, is the exponent. So this would be -2, -1, 0, 1, and 2. And that's because, let me just show you this one, the log base 2 of 1/4 equals the exponent. We noticed over here that if you take 2, a base of 2, raise it to a power of -2, that would flip it over and square it and give you a result of 1/4. So this log expression here is saying 2 raised to what power would give me 1/4? That power would have to be -2. The y is the exponent. So what we begin to notice again is that I have a vertical asymptote. So this function has not a horizontal asymptote, but a vertical asymptote at x equals 0, because it is doing the reverse of an exponential function. It is spitting out the exponent instead of plugging in the exponent. So what used to be y, what used to be horizontal, is now x, or vertical asymptote. So we dot that in here. And you can see the more negative y gets, right, -1 to -2, etc., the smaller or the closer to 0 x gets. So you're going to kind of see how that looks on the graph. So let's go ahead and plot these points. So you can see here as x is getting closer to 0, so x is inching its way to the y-axis, the y values are just shooting straight down, and they're just going to go farther and farther and farther as x gets closer to 0, creating this vertical asymptote. And then it just kind of rises slowly on the right. You can see it's a very similar shape as my exponential function, but in the reverse order, because it's switched. All these ordered pairs have all been reversed. So for those, we always remember the asymptotes and the direction of the curve. Now, of course, both of these were examples where the base was greater than 1, which is the more commonly used version. Now, last but definitely not least was our reciprocal function. And this function was super unique because it was the first time that we had divided by x, the first time we had an x in the denominator. So why was this unique? Because we cannot let x be 0. So this right here became a problem because I'm not allowed to divide by 0. 1/0 does not exist. It has no value, right? So we marked that spot on our graph with a vertical asymptote. The vertical asymptote indicates where the y value doesn't exist. This was the first time that we just didn't have a y value at all. It's not an imaginary number, it's just nothing. It doesn't exist. And that is because we're not allowed to divide by 0, and suddenly we found an x in the denominator. Therefore, x could not be 0. Now for the other points, we just noticed that they're reciprocals of each other. If x is 2 or -2, y is just 1 over that, -1/2. If x is -1/2, y would be -2/1. So it's kind of like when x is big, relatively speaking, y is small, right? When x is 2, y is a half. When x is a half, or when x is small, y is 2, which is big. So when x is big, y is small. When x is small, y is big. It's a reciprocal relationship. So when we plot the points and look at them, you begin to see that kind of play out. So what do we mean by big and small? By big, I mean it can either be going to either a positive or a negative infinitely large number, so far from the x or y axis. What do I mean by small? I mean getting closer to 0. So notice as x goes to 0, right, from both the positive side and the negative side, going to 0, the y values are either going up, so big positive, or straight down, which would be like a big negative, maybe like a negative infinity. So notice that. You get closer to the x-axis, the y shoots up or down, far away, getting bigger. And vice versa. When x goes away from the y-axis, so x is getting big, right, heading toward positive infinity, what is the y doing? It's getting closer to 0. Y is approaching 0. It's getting closer to and wanting to go to the x-axis. Similarly, as the graph goes this way, right, the x value is heading to the left, so it's like a big negative. The y value is wanting to come up here to 0 again, right? The y value wants to get close to 0. So it's just this kind of reciprocal relationship. When x is getting bigger, y is getting smaller, and vice versa. So it ends up creating another asymptote, the horizontal asymptote. So this graph is unique because it has 2 asymptotes. It's got the vertical asymptote at x equals 0, and that was because we weren't allowed to let x be 0. But then it also has this horizontal asymptote at y equals 0. And that's because it's more of an end behavior type deal. It's more like the bigger x gets, so as x approaches infinity, so as an example, we could have like 1 over 1,000, right? So because y is equal to 1 over x, right? So this is if x was 1,000, then y would be 1 over that. So x is big, right? But 1 divided by 1,000 is super small. In fact, it's very close to 0, right? Getting closer to 0, but it doesn't equal 0. That's not the same. It's just getting closer to 0. So we call this end behavior because x equaling 1,000, I mean, that'd be like way down here, way at the ends of the axis. The y value wants to be 0 so bad. It's like an end behavior type situation. So it causes these asymptotes in the graph and then these opposite facing curves. A very unique shape function. Okay, so before we move on to graphing these with transformations, I just want you to take a good look in at all of these functions and all their connections. We've got our linear absolute value that are both degree 1 with their constant slopes, straight edges. We've got our everything else, which is curved, but we have our quadratic and cubics, which make the parabola that opens only up, and then this squiggle, or lazy S, that kind of makes a little squiggle through the origin, can go up and down. We've got our square root and cube root that are sort of doing the reverse of squaring and cubing, creating sort of these sideways shapes. Of course, the square root can only go right and up, so it looks kind of like an eyebrow, whereas the cubic can kind of go in all directions, but it's kind of like a sideways squiggle. We've got our unique exponential and logarithmic functions with their horizontal and vertical asymptotes. And then, of course, our reciprocal function that had both the vertical and horizontal asymptotes, and then these opposite facing curves. All right, so now let's go on to page 2. Okay, so before we start graphing these functions, I want you to notice something about all of them. Take a look at all 9 of these. Right now we're just looking at the first 2, although maybe I'll show you the second 2. You might be noticing that they all have the same a, h, and k value. A is -1 for all of these. H is 5 for all of these, because remember, H is opposite sign. And K is 4 for all of these. So I'm going to be doing the same graph transformations, but just with a different parent function each time. So our job is going to be to recognize and execute the correct parent function with transformations for each of these. So because the a is negative, that means each of these are going to have a vertical reflection from their parent function, right? The parent functions are on the first page. These are going to have a vertical reflection from each of those. Each of these are going to move 5 units to the right from the center, from 0, 0. And each of these are going to move 4 units up. So for number 1, though, number 1 is just linear. We know this because it just is raised to the power of 1. So for this one, I don't really need transformations. I just need my point, which is hk, which for all of these is 5, 4, and my slope, which is the a value, which is -1. So I'm just going to plot the point 5, 4, and then from there just go down 1 and to the right 1. Or I can go up 1 and to the left 1 to continue that same constant slope. And there is the graph of my line. Now for number 2, that one's an absolute value function. So again, I don't really need the graphing transformations. I just need the vertex, which is hk, which is 5, 4. So I'll plot that. And the a value, which will give me the slopes. So the a value is -1, so that means I have my first slope is -1, but my slope on the left is the opposite of a, so that'll be +1. So I know that this graph is going to open down. So from my vertex, which is 5, 4, which is the middle, on the right, I'm going to go down 1 into the right 1. And on the left, I'm going to go down 1 into the left 1, actually creating a positive slope. So it looks like the parent function, except opening down because of the vertical reflection and shifted right 5 and up 4. So now for this one, we know this is the quadratic because it's got the power of 2. So we know the parent function is going to look like a parabola. We also know that this graph had a vertical reflection because a was -1, and that it's going to move to the right 5 and up 4. So it's going to look something like this, just based on what we know the parent function to look like and the transformations to cause. So why don't you go ahead and find the points for this and plot them. So sure enough, we can see that our points gave us the same graph. By adding 5 to all the x's, multiplying all the y's by a, which is -1, and adding k after that, I got these points, 3, 0, 4, 3, 5, 4, 6, 3, and 7, 0, creating my parabola that has the vertex at 5, 4, which we knew, and opening down, which we knew. Now number 4 we can see is our cubic, right? The one where you raise x to the 3rd power. I can see that because the power is 3. Again, it has the same transformations. So I know the parent function looks like this. And I know that this new function is going to take that graph and reflect this part down, making it kind of go like that, and reflect this part up, making it go like that. That's what the a being -1 does. But then it's going to take this and slide it to the right 5 and up 4. So I know my final graph should look something like that, again, just based off the parent function and the transformations. But why don't you guys go ahead and fill out the table and plot your graph? Very nice. So we can see that the points did in fact produce that graph that is centered at the hk of 5 and 4. Of course, that's where the point of inflection is. And has the points 3, 12, that was this one here, 4, 5 right here, 5, 4, that's the middle, 6, 3, and then 7, -4. We found those by using our transformation rules. You add h to x, you multiply a to y, and add k. So looking at 5 and 6, we have our square root, because the index is 2, and our cube root, because the index is 3. So I know the square root function is the eyebrow. It starts at 0, 0, and can only go up and to the right from there. Whereas the cube root starts at 0, 0, but it can go up and to the right and down and to the left. So it goes all along both x and y axis like that. Now both of these graphs are going to have a vertical reflection, so they flip underneath or over the x-axis. So this eyebrow flips down, becomes more like bags under the eyes. And they're both going to scoot to the right 5 and up 4. So this will be kind of like that, our final graph. The cube root, when you reflect it over the x-axis, this top part goes down and kind of looks like this. But then the bottom part, the part that was negative, goes up and kind of goes like that. So it's going to look something like this when we vertically reflect it. And then this middle point is going to scoot to the right 5 and up 4. So it'll look something like that. So go ahead and use the transformation tables to get the points for these final graphs, which we know should look something like this and this. They have the same center point, but instead of only going in one direction, the cube root can go down and also up and to the left. Go ahead and find those points and plot them. So after finding my points for the square root function, which ended up being 5, 4, that's our starting point, right, our HK. And then 6, 3, 9, 2, and 14, 1. I actually didn't graph that. I stopped at 9, 2. But you can see that shape that we expected it to be. The eyebrow, that's going down now and to the right. And then for number 6, again, I had the points -3, 6, 4, 5, and then 5, 4, of course, is our HK. That's our middle point right there, our point of inflection. And then 6, 3, and then 13, 2. And we could see that sideways squiggle that's now kind of going down and to the right. So those are our graphs for our square root and cube root. So then in 7 and 8, we see our exponential function because x is in the exponent. And we see our logarithmic function. So it's very important that we recognize that the base is 2 and then make our parent table of values based off of that, because that is what we will use to graph this one with transformations. So we complete our table, and then we plot these points for the parent function. Of course, we have to also remember, write this in big letters, that exponential functions have a horizontal asymptote at y equals whatever the k value is. So for the parent function, that's at y equals 0, but for this function, when I eventually do the transformations, that's going to be at y equals 4. So the parent function, this one, you have your horizontal asymptote at y equals 0, and then you have these points. So that is our parent function curve. Now we know that this one is going to have a vertical reflection, so it's going to be on the bottom below the asymptote. And everything is going to shift to the right 5, so it's easier to move this point, or actually this point, now that I reflected it. So that's going to go to the right 5 and up 4. So it'll be like right there, and it's going to be something like that. And this horizontal asymptote is also going to move up 4. So it's going to look something like this. So why don't you guys fill out your table and sketch your graph? So I added 5 to all these x's. I got 3, 4, 5, 6, 7. I multiplied all these by -1 and then added 4. So this became 3 3/4, 3 1/2, 3, 2, and 0. And so I just plotted these points. Now you can see that these ones here are getting closer and closer to 4. So when you're making your graph, you kind of want to continue that trend, like have your arrow kind of climb up and toward your horizontal asymptote, which is now at 4 based off that k value. And there's our graph. Now for the logarithmic one, of course, these are always a lot more challenging. So you again want to recognize your base is 2. And you want to start out with the parent table. And you want to remember what the equation for the parent function would be. So you ignore a, h, and k, just kind of block them out of your mind, and you just think, okay, this is just a log base 2 of x. And what does that mean? That means 2 is the base, y is the exponent, and x is the result. So when you're setting up your table, it almost helps to plug in -2, 1, 0, 1, 2 for the y value, and then remember that x is the result of taking the base 2 and raising it to the power of y. So then after you get your table for the parent function, it helps to kind of remember what it looks like. So I can see here, right, these x's want to get closer and closer to 0. So for this one, we have to remember the parent function has a vertical asymptote at x equals 0. So that's for the parent function, but remember, in general, it happens at h, at x equals h. So we have to now look at the equation. Notice, okay, h is 5, so my new function will have a vertical asymptote at x equals 5, because what's going to happen is, well, let me plot these first. So here's my parent function, right? It kind of stretches to the left toward the vertical asymptote, but doesn't cross it. So what's going to happen is this is going to reflect over the x-axis like this. And then from there, it's going to move to the right 5 and up 4. And the vertical asymptote is going to move right 5 right along with it. So it'll look something like this. So we get that idea sort of in our head, and then we'll make our table of values for this and make sure it's correct. So our ending product will look like this based on these points. So I just took these x's and just added 5 to them. So this became 5 1/4, 5 1/2, 6, 7, and 9. And then I took these y's and changed their sign, right? Multiplying by -1, so then this became 2 plus 4 is 6, 1 plus 4 is 5, 0 plus 4 is 4, -1 plus 4 is 3, -2 plus 4 is 2. I plotted those points knowing what the shape should roughly look like, knowing that on the left it should kind of reach toward that vertical asymptote. I dotted in my vertical asymptote at x equals 5, or whatever the h value is. And voila, there is our graph. Now last, but definitely not least, we have our reciprocal function. So this is the one that we know has the vertical asymptotes and then has the opposite facing curves. Of course, this one's had the reflection. So we know, first of all, that the vertical asymptote is always going to be at h. So we know this will have a vertical asymptote at x equals h, which is 5. And then the horizontal asymptote always happens at k. So this one will have a horizontal asymptote of y equals 4, because k was 4. So the x is based off h, and the y is based off k. So I know I have a vertical asymptote here at x equals 5. I have a horizontal here at y equals 4, and I know that my curves should be on the opposite sides, right? The parent function is usually like this, up on the right, down on the left, but this one's had a reflection. So this part flips down here and goes like that. This part flips up there and goes like that. So when you have an a value that's less than 0, which in this case it is, it equals -1, then the curves are on opposite sides. So I know it's going to look something like this, but again, I'm going to do my table of values to get my points and then finalize my graph. Okay, so here's my final graph with these points plotted. So I just took the parent function values from our first page of notes. I added 5 to all the x's to get these numbers here. Remember though, this middle one is where y is undefined. That's where my vertical asymptote is. So it's not a point on the graph. It just sort of marks where my vertical asymptote would be. So I had 3, 4.5 right here was that point. 4, 5 right there, and then 4.5, 6. So it's kind of right there. Kind of forms that upward facing curve on the left of the asymptote. I skip over the asymptote, and then I had 5.5, 2 was right here, 6, 3 right there, and 7, 3.5 right here. And then that formed my sort of downward facing curve on the bottom right. And so there's my graph. That concludes our lesson. Whew, this was a long one. Thanks for sticking in, and I'll see you in class. Bye.